Good morning. It's a pleasure to be here. Thanks, Mary Ann and the organizers for inviting me to speak. I had a great setup in the previous two talks. I'm going to talk mainly about exascale computing and give you some idea of where we think we're headed with exascale computing, and give you some projections about what an exascale system might look like. And then try to back up and think, okay, now that we assume we're going to have a system that looks like that, what are we going to do with it? How are we going to program it? What are the parameters for the storage and memory? How is that going to change the way that we work? Just as an overview, the challenges I'm going to discuss include things like the power issue, and I'm sure many of you have already heard about that from other sources. There's the memory capacity and bandwidth. We're looking at memory capacities to be much smaller in the time frame of exascale unless there's some new technology. Parallelism. We're talking about billions of threads potentially that's available in your system, and they might be efficient at doing 20 flops. You just create a thread to do 20 flops and then it disappears. How would you change your algorithms to make use of that? And then finally, one of the major challenges that's probably most relevant here is this idea of programmability. How is this going to be exposed to the user? And that's a critical challenge because many people in computational science already have large codes that they've created. How are they going to take those and move them forward to the exascale era? So I'm going to talk about some of the programming systems that we're currently using and where those stand, and then I'm going to dive down on a concrete example. And the concrete example is graphics processors. So if you've been to any conference over the past 2 years, you know graphics processors are really a hot topic. Right now, everyone's really programming them manually. They're using CUDA or OpenCL to program the system, and that takes some specialized knowledge. The hope is that over the next couple years, next 5 years, we'll be able to develop tools to hide some of that complexity from the user. I'll talk about that in detail. And then finally, I will mention some of the ecosystem issues around that. I mean, you don't develop a new application in the absence of software tools like libraries and debuggers and things like that. So I'll briefly mention those as well. And feel free to ask questions along the way. So toward exascale, if you're a member of the DOE community, you've probably been involved in one of these workshops over the past 3 or 4 years. There have been an extensive number of workshops focusing on things like climate science, nuclear energy, as well as cross-cutting technologies. And David Brown, Paul Messina, two people who are here today, led an important cross-cutting technologies workshop that looked at the mathematics, the computer architectures, the software systems that we're expecting in that time frame. Then there have been a number of might change. Okay, there we go. Thanks. There have been a number of other steering committee and software project meetings that I'll direct you to so you can go learn more about these predictions. In any case, did it die completely? That's okay. Testing, there we go. So, so just to back up, one of the great things about these workshops has been the fact that we've taken a holistic view of the whole software stack and applications and architectures. And if you look at it, it ranges everything from applications and the way people use those applications. And what I mean by that is, do they do uncertainty quantification? Do they run the same job with slightly different parameters thousands of times and then take the output from that and make a decision? That's a usage model. Then you have all the different applications. An important part that I'm going to talk about in detail today is the programming environments. How do those change? How have those changed over the past decade? Then there's the system software. This is the file systems, the scheduling, the things you know when you use Linux to do something on a node. And then finally, the exciting part that I'll talk about first is the architectures. And everyone knows about multicore. But the graphics processors, as I said, are a hot topic. And then there's FPGAs and a variety of memory models that users have access to that are going to change the way we work. So let's just look at where we are today. If you look at contemporary systems, this is a list of some of the most recent systems, and I'll talk about a few of those in more detail in a moment. Some of the most popular systems are NVIDIA-based. They use graphics processors. And then they have basically a commodity interconnect. One of the things you want to look at here is the peak floating point operations. And Tihani 1 a year ago was #1 on the top 500 list because it had 4.7 petaflops in a relatively small footprint and low power envelope. If you look at some of the newer systems, the K system, which I have an extra slide on, it's also a very impressive system and came in at an incredibly high LINPACK rate. It's in a partially completed state, and it's almost 9 petaflops. And that was almost slightly more than 3 times what Jaguar is at Oak Ridge right now. And so that was a very impressive feat, and it's not completely finished yet. It takes about 10 megawatts to power that system. Some of the systems on our horizon include Blue Waters, I'll mention that. And then Cray Titan, which is a GPU-based system that will be at Oak Ridge. Then there's Blue Gene Q as well that'll be available at the other, at Argonne and Livermore. So just to dive down on this a little bit, if you remember back when the Chinese built several GPU-based systems, this one was the most recent. It used about 7,000 Tesla M2050 cards. And those were used in conjunction with 15,000 Wismirs to create 4.7 petaflop peak system. So that's not in and of itself a major feat. We could have done that with many other technologies, but the catch is that they fit all that in about 4 megawatts. And if you look at facilities that are available today, 4 megawatts is substantial in terms of the heating and the power that you need to bring into a building to be able to run a system of that scale. In fact, they estimate that if they didn't use GPUs to get the same capability, they would have needed almost 12 megawatts to get the same performance on LINPACK. Now, if you look at K, and this was just last month, the K supercomputer in Japan, which is, like I said, partially complete. It's 672 racks right now, but they're planning over 800 racks of this, and there's an actual picture of it. It came in as #1 on the top 500 list. It was 8 petaflops on LINPACK, and that is that's an impressive feat, not only in the raw number, but in the percentage of peak they were able to get out of the system. It's also got a very large number of processors and also a correspondingly large amount of memory in it. If you look at the chip itself, it's an 8-core modified Spark 64. Everyone thought Spark was dead, but the Japanese took this particular chip, added vector units to it, and made it a very impressive supercomputer chip. It's 128 gigaflops in about 58 watts of power in that 8-core chip. That is the heart of the K system. Another system that you're going to see on the horizon and is starting to roll out is this Blue Water system, NCSA. It's an NSF system. That system is based on this Power 7 chip that you can buy. It's also 8 cores, about 32 threads. It has a very impressive memory bandwidth of 128 gigabytes per second. You take all those and put them together and ramp up to about 10 petaflops. Now, the system is just starting to be installed now, and nodes are starting to roll off the factory floor. But when it all's said and done, the system will have 10 petaflops of peak. They're expecting at least 3 applications to have more than 1 petaflop sustained. It's going to have over 300,000 cores. So you can see these things increasing. The peak, floating point rate, the power, the amount of memory you have is increasing some, but not at the same rate. So that gives you an idea of there are multiple architectures people are looking at in addition to just your normal x86 clusters. There are now projections about where we're going to be for an exascale architecture. So if you look history and try to predict where we're going to be using some of the technologies that are available there today, out there, or predicted to be available out there in the next decade, one of the output, one of the items that we took away from our architecture workshops that we had earlier was this chart. And this chart is valuable for several reasons. It gives you some idea of where we are today, and this is essentially Jaguar in this slot right here. It's about 6 megawatts of power. It has about 300 terabytes of memory. Your node performance is about 125 gigaflops. And then you start trying to reason about where you're going to be in 2015 and 2018. 2015 is considered to be an intermediate machine. 2018 is a true exascale peak system. If you look at that and you try and project out and think about it, some estimates for this 2018 system using conventional technology had a power usage between 100 and 400 megawatts. And I said that properly. It was 100 and 400 megawatts. If you just assume that most power for systems like these cost about $1 million per megawatt year, you would need at least $100 million just to keep the power on for the system if you use conventional technology. That's not sustainable and not practical in our current, well, in many environments. And so basically, people, experts said, okay, let's give a target of 20 megawatts and see what we can do with 20 megawatts. And that's really looked at as a constraining feature. It's not that we don't know how to pipe a half a gigawatt into a facility. I mean, you do that for various reasons, but that is really the constraining overall overriding factor. And that really drives the rest of these choices. If you look at the amount of memory you have, it's substantially less per core than than earlier systems, 32 to 64 petabytes. If you look at the node performance, these are broken apart because they're really what we referred to in the architecture meetings as swim lanes. There's 1 teraflop and 10 teraflops, and probably fall somewhere in between there, but really it had to do with different architectural models. Do you believe in the GPU model that has a lot of floating point operations, or do you believe in a more standard model to be available in that time frame? And then you look at other things like memory and node bandwidth. The concurrency is something else that's also bounded. If you look at the concurrency, it's 1,000 to 10,000. Now remember, if you look at something like Jaguar today, you can run 12 threads concurrently. If you look out to these future systems, you're starting, and this is a node, this is not the system, this is just a node. In 2015, 100 to 1,000. In 2018, 1,000 to 10,000 threads of activity are happening inside of the node itself. And then you take thousands of these nodes and put them together. So let's just pull all that together and think about what an exascale system might look like. So this is a slide from the NVIDIA Echelon team, which is a DARPA UHPC project. And what we've done on that project is put this cartoon together that describes what a system might look like in that time frame. It looks very much like a tightly integrated GPU system. If you look at this, what these mnemonics mean, the LOC is a latency optimized core. So you can think of that as an x86 type of core that's still on the actual chip to do things like I/O and file I/O and really serial tasks that the other cores aren't good at. And then along with that, you're going to have these streaming multiprocessors that look very much like a streaming multiprocessor in a GPU today. They have a lot of lightweight, low-energy cores that give you a lot of concurrency, and they hide that latency that you have to the memory system by switching between the threads to keep busy. You take all of those cores, put them on a network on the chip, and you connect them up to a memory controller, some cache, and then the interconnect. And the memory, by the way, is your normal DRAM, but there's also a place for non-volatile memory. So you've seen the flash memory that you can buy in the store, 16 gigabytes for $16. It probably won't be the same type of technology because that technology isn't reliable over time. But there are several other memory devices like spin torque transfer memory, phase change memory, those types of things that will probably be an important part of an exascale system. And the primary reason for that is their low energy usage when they're not being used. DRAM, on the other hand, needs to be constantly refreshed, and it takes power to do that. So even if you aren't using the memory, it's using energy. And so it's more of an energy play than anything. Then you take seven of those nodes, put them together on a module, put those together in a cabinet, about 15 of them, tie them together, and you have about 400 cabinets. You have an exascale system. So that gives you something to work from when we're thinking about a 2018 exascale system. Just finally, if we look at this uneven impact on system balance, excuse me, the system peak is going to go up by 500, but then all these other factors are going to change as well. Concurrency, we've already mentioned, will go up dramatically. Other things like the total system capacity, memory capacity, might only go up by 33. Your I/O bandwidth and storage might only go up by factors of maybe 20 or 100. How's that going to change the way you do computational science? Will you even think about writing out your entire data set to analyze it later, or will you have to analyze it in memory, in situ, and determine your result from that? That's something to start thinking about, and what the co-design teams that Tim and I and others are on are starting to seriously consider. So just to summarize, if you go back and look at some of the challenges that we see to exascale, system power is a primary constraint. Sure, we can build a big facility and put a bunch of cabinets in a room, but to be practical about it, we really need to manage power. Memory bandwidth and capacity are not keeping pace. The concurrency is growing like gangbusters. No one knows what the processor architecture is going to be. Everything's pretty much a cartoon right now. And then the model itself, and this is what I'm going to focus on later, is really an open question, and you see a lot of new solutions being proposed right now to answer this question. So let me take a few minutes and talk more specifically about power and why power is the driving constraint. So this is an experience slide. So at Oak Ridge, about 7 years ago when I joined, we had a brand new building that had 40,000 square feet and about 15 megawatts of power piped into it. And we populated that with a Cray X1 and then, the X1E, and then several other XT4s. And now we have Jaguar, which is the DOE system, and Kraken, which is the NSF system, and a few other systems on the floor there, and it's basically full. It's not that we don't have the floor space, it's that we don't have the power to be able to power big systems in that building. And that's led us to do things like build additional buildings in that amount of time and think about just how big we can keep going on this trajectory. Are we going to have to build a new building every time we want to build a supercomputer? And if you look around the world, basically, that's what's happening. The Livermore and Los Alamos, Blue Waters needed a new building. In China, they had to build a new building because they wanted to put one of these new systems in it, and they didn't have the facilities or the resources available elsewhere to do it. The other thing that's driving power, and this is an entirely different trend. This is your cell phone. This is Moore's Law coming together. This is looking at a slide from ARM that illustrates it perfectly. It's called dark silicon. It's basically, when you look at the process for developing semiconductors today, Moore's Law is going to continue. We're going to have more transistors that we can put on a chip. That's not a big problem. The problem is that, and this top graphic illustrates the amount of area that this same functionality would take up in a chip in 2020. It would be 1/16 of that chip. If you look at, on the other hand, the power budget and how that's shrinking, basically what this is showing is that if you want to keep power constant or slightly less due to some of the physics characteristics of silicon, you have to leave part of the chip powered off if you want to run that small part at the highest clock frequency that you can. And so what that essentially means is today you can power this chip and keep it, for the most part, everything powered on. Out in 2020, you're only going to be able to run about 10% of the chip at the clock speed that it's expected to run at. Meanwhile, everything else is going to be powered down, and that's why it's called dark silicon. And this is important not only for us, it's important for cell phones, it's important for a variety of reasons. So what people are thinking is, you put specialized functionality in here. You put a GPU, and then when you're not doing GPU-oriented computations, you power it off for a couple microseconds, and then when you need it again, you turn it back on. And this is coming true. If you look at your Xbox 360, it's just not commodity components, it's a system on a chip. It has 3 cores in it, plus a graphics core, plus a bunch of interface technology to allow it to talk to things. But it helps keep the power down. It keeps performance up. That's the reason they do that. If you look at just a chip from AMD that was announced last month, in fact, it's exactly what we've been talking about. This is a chip you can buy today. You can buy notebooks with it today that have 4 x86 cores, and then they've taken a bunch of Radeon cores from their graphics line and just put them right on the chip, so it's all on the same chip. And the reason for that, and you can talk to people at AMD and Intel and other places, is just to keep the power down. They have all that functionality there and available transistors, so you're going to see more and more of this. And that little chip itself in single precision can give you up to 500 gigaflops of processing power. That's huge compared to that's huge compared to where you would be if you were only using the 4 x86 cores. And it's only in 45 watts, the thermal design point. So I'm going to dive down and just talk a little bit about the emergence of graphics processors that we're seeing today, because I'm just curious, has anyone programmed in CUDA in this room? So, okay, we got, a few believers already. So let me tell you why some of this is happening. If you look around, as I mentioned, around the world, there's a number of GPU-based systems emerging. Tokyo Institute of Technology, several in China, there are several here in the US, and then of course Titan is planned at DOE at Oak Ridge, and that should be between a 10 and a 20 petaflop system. The reason for that is this. We've had programmable graphics processors for about 10 years. So you've got them in your laptops, you can go to Best Buy and buy a 1 teraflop board for $200. And that's commodity. They've always had high single precision floating point rate for graphics. They've always had very high memory bandwidth. They build their own memory for these called graphics GDDR. And that in turn gave them a high flop per watt ratio, so they could keep it down to keep the power down to put in things like desktop systems or game stations. But things really started to change on the right side here. About 4 years ago, they introduced CUDA. And so CUDA, before that, programming GPUs was a nightmare. I mean, you had to know OpenCL, you had to know the constraints on the architecture. You had to write it basically like a graphics application and try and get your algorithm to fit. CUDA is essentially an extended C. And so although you still have some constraints on your actual things that you can do, like memory accesses and things like that, it looks pretty much like C. And then OpenCL, which I'll talk a bit more about in a moment, was a standard so that it just wasn't NVIDIA specific. It was heterogeneous computing in general, and you didn't have to recode your application every time you wanted to move to a different device. And then the couple other things that are specific to Fermi, which is NVIDIA's latest graphics processor, is it added error correction. I mean, if you think about this, why in the world would you have error correction in a graphics processor if it was in a consumer desktop box? It costs in terms of power and transistors. Don't put it in performance sometimes. And so Fermi added that, so you can turn it on and turn it off, but when you put 10,000 of these GPUs in a system and start running an application, you're really worried whether it's going to give you the right answer or cause your application to crash every time you start to run. And then finally, Fermi, as I mentioned earlier, most graphics processors had high single precision, but they had an eighth or a tenth of the double precision performance of single precision. Fermi changed that, so now it's just a half. So when you have a teraflop in a GPU, you have about 500 gigaflops of double precision in a GPU. And so that's another change that's happened that's quite relevant. So I'm not going to dive down into this in too much detail, but the architecture of this is important. It's important to understand why things are going this way. They've created all of these simple cores, and these aren't cores in the terms of an x86. They don't run Linux. They can't run a lot of things that a normal x86 core can run. But they're very good. They can load, thread, execute a few floating point operations, do a few load and store operations, and then basically be retired. And you have hundreds or thousands of these potentially on a GPU chip in and of itself. And this, by the way, is IEEE standard floating point. Earlier chips didn't even have that, so you had to play games with accuracy and those features of your application. So one of the systems, and this is a system that we've installed at Georgia Tech for NSF, just to give you an idea, it looks very much like a standard Linux cluster. In fact, you could use it just as a standard Linux cluster. However, it has 360 Fermi graphics processors in it. And those graphics processors give you a huge capability to do applications, because you go from just having 67 gigaflops in your Xeon to having 515 gigaflops in your M2070. And you take those and put those together, and this 7-rack system has 200 teraflops of computing capability in it. That's 90 square feet, and it's under 100 kilowatts. And it is, for the most part, a commodity-based system. Some of the applications, and I have several application slides in here because people always ask us what applications perform well. Are there any real applications running on the system? And we certainly have some. We early on experimented with computational materials and saw some nice speed ups there, and this is about 3 years ago, but we would see a speed up of about 5x for the overall application. There's a combustion S3D application that the chemistry kernel, we were seeing speed ups on the order of 16 to 31, and then overall application performance of about 2 to 3x, depending on what chemistry was being used. And so those numbers aren't dramatically impressive in terms of some of the speed ups you hear, 300x or something like that. But when you think about them from the power point of view, they are impressive because you can do a lot of the same work in less power. So some others, there are some very impressive examples, and most of those come from the molecular dynamics community and the bio community. And this chart is right. Basically, because some of these problems are strong scaling problems, especially from the bio area, these software codes like Amber, Amber 11 has recently been ported and optimized for GPU. You can do the same amount of work on a 4 GPU system that you could do on about 300 CPUs of a system like Ranger at TAC. And so there are very good examples of where GPUs are impacting science and being able to have high throughput science on these systems. Others, Lattice QCD, and these will be in the slide deck, and you can look at them. I just wanted to give you the breadth of apps that we're looking at. And then, of course, there's LAMPS. Many of you are probably already familiar with it. It's used for materials modeling and bio and various areas. It also shows a nice speed up with the GPU acceleration. So what have I told you so far? So I've tried to give you some idea of where we are today in computing and what we're expecting from Exascale and what the parameters look like they're predicted to be. And then we talked a little bit about the concrete example of GPUs, and because it's happening today. GPUs are real. People are trying to meet this power issue now. How are they doing it? And how are they programming them? And so now I want to use that as an example of programming. So as I mentioned earlier, with this slide, the applications are what you do. You have to do things that are important for science. You have to, choose particular areas that are important to your sponsors, and develop algorithms and codes that work on them. On the other end of the spectrum, you have the computer architects, and I've tried to motivate what their goal is. They're trying to do things like manage power and build cell phones and supercomputers out of the same chip sometimes, GPUs, DSP chips, things like that. So in some ways, they have different incentives than the people doing the applications work. The real crucial part of this is the programming environment. If you think about all the features that you can have in a programming system, like domain-specific libraries and frameworks, even languages and auto-tuners, those can be leveraged to hide a lot of this complexity from you. And that's what I'm going to talk about in a few minutes with respect to GPUs. So if you look at the state of programming systems today in HPC, what you see is a list of a lot of things you guys probably already know. C, C++, some version of Fortran, MPI and OpenMP. Lately, CUDA and OpenCL have started to be used to program GPUs. And then, of course, people use things like Python and Unified Parallel C, Co-array Fortran on a selective basis, and it's very application specific. But you see those, and those are things that we can point to as examples that are in use today. Now, the future is completely open. If you go to some of the reports I mentioned earlier, there is a diverging opinion about what programming models are going to be in the next decade. There are things out there like global arrays and Charm++, stars, Silk, thread building blocks, concurrent collections, parallel MATLAB, and people are really starting to try to figure out if some of these tools offer a layer of insulation between all the complexity of the hardware and what their applications are trying to do. And then, of course, it's always nice when you have libraries like BLAS or LAPACK or Trilinos or FFTW that does some of that for you. But right now, even those guys are struggling to understand how to map to things like GPUs that have sometimes very diverse architectures. And this is a slide from Brad Chamberlain that I saw a couple weeks ago. And really, if you think about it, in HPC today, there are the two dominant models, MPI and with some OpenMP. And for the most part, MPI is just completely dominates the HPC space. Part of the reason for that is you have distributed memory, but you're in charge of managing that distributed memory. There's no, if you put a piece of data in the wrong location and then have to later suffer a long latency to go get that, that's something that you have to address if you want good performance. If you look at OpenMP or Chapel, for example, sometimes it's not so clear to the programmer how to optimize those applications and to know what performance to get, even if you do write a very short code that allows you to be productive in your applications. And the overall question that I'll throw out here is it's kind of the quest for compiler and language people in general, is this idea of, is it possible to write one application that runs efficiently on all architectures? In one language, you write it once, and then you run it everywhere. And the key is not just run it, but you run it with some reasonable amount of efficiency. And that's the real challenge. And that's a big challenge for OpenCL that I'll speak about in a minute. The graph here is from a DARPA HPCS study that we did about 5 years ago. And basically, we implemented, and a bunch of students, rather, implemented the NAS parallel benchmarks and the HPC challenge benchmarks in different paradigms. So here it's Fortran C plus MPI and Fortran C plus OpenMP and Java. And then this speed up is relative to what the serial implementation is. And then the relative code size in lines of code is the horizontal dimension. And what you see is a progression toward more lines of code equals more speed up. And so that's really not what we want to do. We want to have better speed up while keeping the code size constant or flat. And right now, that's not what we're seeing. If you look at this MATLAB example, there's serial MATLAB has some possibilities, but there are pMATLAB, which is parallel versions of MATLAB, that automatically parallelize your code or you add directives to. And you see some speed ups there, but when you jump to C and MPI, you see even better performance, but you also see more lines of code. And so, right now, intuition is telling us that we can't do this. There's not really a good way to write one application that runs efficiently on all architectures. But we're optimistic. We're scientists after all. We think there's some way we can solve this problem, and it's an important problem. So if you just think about programming systems in general, these are the main challenges. First, how should we expose multiple levels of parallelism? Because it's not just one. It's not just instruction level parallelism. You're talking parallelism on the node, at the instruction level, at the MPI level, and perhaps across multiple applications running in concert. Second, how should the communication occur? Should, you have to send a message and have the receive write the code that receives it and unpacks it on the receiving side? That seems like a lot of work. I mean, people have complained about MPI for a long time because it also is performance, has performance implications where if you don't orchestrate the data properly, you just trash your performance. Another question is, should thread data locality be exposed at the user or managed by the runtime? And that is, is there a clever way to have the runtime system schedule your data to be there when you need it? And that's a complicated question that a lot of people have wrestled with in the compiler community, but perhaps if we change programming models, that's something we can do. Next, how should we best enable domain-specific libraries, frameworks, and languages? I really believe that without this next level of insulation, it's almost impossible to solve that overall goal that I mentioned earlier. And then finally, how do we maintain legacy applications and software? So you've got, hundreds of millions of dollars of investment in software. Do you just throw it all away and start over? Most people think not. You have to have a way to preserve some of that investment. So that's where I want to dive down into GPUs. We could talk about Exascale, but some of these trends are emerging today in GPUs, and so I just wanted to do a quick case study of where things are going with GPUs. If you look at a typical GPU software environment, and this is very much like the Keeneland system that I mentioned earlier, it's integrated with the TeraGrid on the NSF system. It has a programming environment that has GCC and Intel compilers, all of those things. But it also has the CUDA software development kit, the OpenCL software development kit. We have a host of GPU-enabled compilers there, as well as debuggers and tools and libraries that work in concert with the GPUs. One of the things we're finding is that we have 5 different compilers right now that we're testing, and the performance of them is changing very rapidly. And I'm not talking about 10 or 20%. I'm talking about orders of magnitude change in performance based on a new update in the compiler framework that we have. There's also a lack of software development tools. And whenever you have a fast-changing world like you do in CUDA and OpenCL, the tools are always going to lag a little bit behind. But it's critical. If you want to be able to write code, you're going to have to be able to turn on a debugger and step through it and find out where you're having problems or link into some library that provides that functionality for you. So just to again do another dive into where this is going and what the community is doing about it. Everyone's familiar with CUDA. Well, about 3 years ago, OpenCL was created, and it's an open standard. So anybody can implement it, and it can be implemented on any platform because it's an open spec. All of these companies, including NVIDIA, Intel, IBM, several others, got together to create this because they think it's a very, very important problem. Now, the way to think about what we're trying to program here and the levels of abstraction provided by OpenCL is this. You have some host that provides some of that basic functionality, like I mentioned earlier, basic operating system functionality and so forth. But it has a number of devices hooked to it, and each one of those devices is essentially in a hierarchy, and you can control and talk to each one of them, and then each one of them has a processing element on it, and you basically decompose it down to a level where you can run these kernels on it. So if you know anything about CUDA or even programmed in OpenCL, the basic way to think about it is you have these arrays of data and what they call an ND range in OpenCL, or a dim block in CUDA. And then those get broken out and basically scheduled by the runtime system, and that's scheduling your kernel. So if you write a kernel, and it might be 5 lines, it might be 100 lines in CUDA or OpenCL, and then the runtime system takes that and maps it on to these data elements and performs some computation on it. That computation has to understand the memory hierarchy, and if you look at this graphic to the right, this is to give you some idea of what the memory hierarchy looks like, because it's a lot different than you have on a traditional SMP. On a traditional SMP, if you write an application in OpenMP and you take a pointer and you hand it to a different thread, that pointer can access it and guarantee you that the memory is consistent and that you're not reading old results and that caches are updated and many of those things that we take for granted today. In a GPU type system, you basically have to schedule all this. So you have to pull a piece of data out of global memory into the perhaps the on-chip global memory, or put it in the local memory of your compute unit, which can't be seen by compute unit N. It can't access this data. And so you have to schedule all of that data transfer if you write this manually. And then you have to actually schedule the work onto these different compute units and basically use the local memory register files and such that you have in that compute unit. So just with that as a summary, I wanted to talk and show you some of the impact that this is having on the environment we're in. Couple years ago, I guess it's almost 3 now, we've created this SHOC benchmark suite. And if you want to learn about OpenCL or want to learn about CUDA, I'd recommend you take a look at it, because what we've done is implement several basic kernels like stencils and matrix multiply and FFT in both CUDA and OpenCL. And we're using that to basically track the performance and understand not only the performance of different GPUs, but what the differences are between OpenCL and GPU performance and how that's changed over time even. So if you look at something today, for example, the single precision molecular dynamics, what you see is these are NVIDIA GPUs on the right. This one is a very low power one that's used in small entertainment types of devices, but it runs CUDA and OpenCL. So you get 1.42 performance on that, but it's a very energy efficient solution. When you go to something like the Fermi that's in the Keeneland system, that bumps up to 27 gigabytes per second in terms of how much data is being transferred back and forth. Then if you look at the GTX 480, which is a gaming system that doesn't have error correction, as well as the 580, you see, getting very impressive performance on those. And then the ATI Radeon, we're also running, and that's an OpenCL capable system. We're getting decent performance on that as well. You can't run CUDA on an ATI system, and you can't run CUDA on an on an Intel system. So this is important in its own right. Some of the other kernels we've added, and this is again another performance example, if you look at something like Sparse MatVec, which I'm sure many of you are familiar with, you know, we coded up 3 different versions of the Sparse MatVec using the different data layouts and found that on the AMD FirePro, on the NVIDIA Tesla, and on the Xeon, we got a different winner for each one of those based on which data layout we used. And so on the FirePro, it was very high performance for the vector layout, and on the NVIDIA Fermi, it did much better for the LPAC format. So that gives you some idea about the performance portability. You can see dramatic changes in these devices based on some small changes in the architectures. The other thing I mentioned was comparing CUDA and OpenCL. So this is the question we've been asked almost every time we give a presentation is, should I switch to OpenCL yet? I've been programming in CUDA. I've spent a lot of time programming in CUDA. And so these slides are a few months old, but early on we were seeing dramatic improvements in OpenCL performance. So what you're looking at on this graph is the difference between version 2.3 and version 3.0 of OpenCL. And so in just that upgrade, we saw a 3x improvement in the FFT that we run using OpenCL. With MD, it wasn't 3x, but it was significant, a significant improvement. If you look at many of the kernels in SHOC, we see that if you think CUDA being you know, the best or the baseline, we see that even today we're very close for several of these benchmarks like sorting and reduction, S3D, and close for some of the others. A few of them are way off, and we actually know what the difference is now and have made some changes to SHOC to bring those more in line so they're not so extreme. So what's the takeaway point here? The takeaway point is OpenCL was an open standard that you can start thinking about coding to today, and it'll run on multiple platforms. Performance is starting to catch up and be competitive with CUDA. And again, we see it improving every day. So let's again back up and just think about GPUs and just look at the questions. So how should we expose multiple levels of parallelism? Well, right now in GPU world, it's mostly explicit. You don't get a lot of free lunches when you program a GPU today. You write your MPI code, you put some threads in there with OpenCL or P threads, I'm sorry, OpenMP or P threads, and then you map some CUDA or OpenCL offloading into that. How should communication occur? Well, no surprise, it's mostly explicit. You have to do things like your MPI transfers, DMA data over to the devices themselves, and then manage the shared memory or scratchpad memory you have on the device. And you do this, you know, there's not many surprises. You do this by things like tiling, which have been developed for cache-based processors, but you have to bring your atoms into shared memory, compute on a few of them, and then discharge them and bring more in when you need to do the next set of neighbors. Should the thread data affinity locality be exposed to the user or hidden by the runtime? Right now, you know, it's pretty explicit because you have to have the data where you need to use it. It's not done for you automatically. This is the $64,000 question even for the Jaguar and systems we have today. How should we best enable domain-specific libraries, frameworks, and languages? We found a lot of stovepiped ad hoc success stories, but we haven't found a real general solution to how to enable that, that particular capability. And then how do we maintain legacy applications and software? Well, we're partially doing that in GPUs because if you want to do more than one GPU, you can preserve the MPI portion of your code and the OpenMP portion of your code and offload some of that functionality down to the GPU using CUDA or OpenCL. And so that's partially. What would really upset the paradigm is if we had a globally addressable memory in GPUs. So not only can you access the memory of the GPU you're on, but perhaps every other GPU in the system is pointer accessible as well. And that would typically cause you to have to go back and think about using UPC or CoArray Fortran or something that respects a partition global address space when you do that. But right now we're not there. So just finally, I wanted to wrap up and talk about what we're doing. We're looking at some techniques to try to move beyond this explicit programming, because right now it really is a manual type of task. So one of the tools we're looking at is OpenMPC, and basically what it is an OpenMP plus a new set of directives so that you can program a GPU without writing any CUDA code. And so it provides a higher level of abstraction and then some easy tuning to generate these CUDA programs. Se-Young Lee in my group has been building this. He's the original author. He just finished up at Purdue last fall. And now we're trying to see how we can map it into OpenCL as well. Due to time, I'm gonna skip ahead here and give you the crux of what I'm saying. Basically, if you look at OpenMP, it has a defined number of objectives in terms of being able to enable loop-level parallelism or task-level parallelism. What Se-Young has done is added several new pragmas like CUDA, GPU run, so that you can say, here's a function I want to run on the GPU. And then the compiler generates that code for you and generates all the data movement code. If you look at the, an animation didn't work, so that's why I was flipping back and forth. So if you look at the compilation system, the overall compilation flow, basically you input your OpenMP program with some of these new OpenMPC directives into it. It gets analyzed. It breaks out the kernels that you want to run on the GPU and feeds those eventually to the CUDA optimizer. But it goes ahead and generates a true OpenMP program that would run in any case on an SMP. It takes all this, pipes it out, generates CUDA kernels, and links it all together. And basically what it looks like is this. You have your OpenMP directive, and this is what normally you would have in an OpenMP application. And then you have these additional pragmas that tell it basically what to run on the GPU, as well as some other hints. And the hints are the important part because not everything can be derived automatically by the compiler. The tuning framework is an important part as well. If you look at this slide, it compiles this code, it generates CUDA from it, it generates all the data mapping, and does all that for you automatically. If you look at the optimizer, and if you know anything about auto-tuning, one of the big problems with auto-tuning is the search space can grow to impractical sizes. And so what OpenMPC has in it is a tuning framework, and that tuning framework looks at the parameters, especially the parameters of the CUDA implementation itself, and tries to find what works best. Number of threads, how big memory should be, how much data you should have in the different levels of the memory hierarchy. And it actually has a tuning engine that actually can improve your performance. And you can control that here. There's optimization levels that you can use to control that. So just jumping to the chase here, we've implemented a number of benchmarks in this and found that, for some of the benchmarks, we can get near CUDA performance, near manual CUDA performance. And so over here, these benchmarks are similar. We had to rewrite the OpenMP FT implementation to get good performance, but it generally still used the compiler. And then we got better performance on the CFD, hotspot, and backpropagation benchmarks. And there are several, like k-means and LUD, that we just still need more capability in the compiler to be able to match that performance. So in the interest of time, I'm gonna speed through this one as well. But we see, competitive performance. There are some outliers that don't perform well, but being in performance analysis for 15 years now, that's true of almost any architecture, I can assure you of that. And I'm going to skip through this one and finish up so we can get to lunch. So I would encourage you to go download this report if you're interested in this area. This is the cross-cutting technologies for computing that we wrote last year in DOE that talks about many of these challenges. And let me just throw the floor open to questions at this point. Thank you.